So let's move to our reversible reactions involving primary amines, secondary amines, and alcohols, Ca23b. Each of these requires a strong acid because it has a neutral, weak base nucleophile, and the oxygen on the carbonyl gets protonated prior to any nucleophilic addition. Each of these undergoes a standard addition reaction to a carbonyl where the nucleophile adds to the carbonyl carbon and the oxygen which was protonated becomes an OH. That's true whether you start with a primary amine, a secondary amine, or an alcohol. And you notice you've lost a hydrogen from your amine or your alcohol to make this intermediate. And these are transient intermediates in most cases. The transient intermediate in which the nitrogen is added to the carbonyl bond is called an aminal, sort of like animal with some letters reversed. And the intermediate in which the alcohol has added to the carbonyl is called a hemiacetal. Hemi means halfway to the full, which is the acetal. Now, none of these three are stable for most species. Instead, they continue on, or protonation of the OH, since we're still in acid, to give us water as a leaving group, after which time either a second equivalent of the nucleophile comes in the case of acetal, or you lose a proton in the case of imines and enamines to make the final more stable product. In the process, we are eliminating a water molecule, and we can use Le Chatelier's principle to help us make the reaction go forward by removing water or backwards by adding excess water. There's also one specific reaction in the chapter that's not in the chem activity but is based on forming imines as an intermediate, and that is the Wolff-Kishner reduction. It is a reduction in that it decreases the number of CO bonds and increases the number of CH bonds, and it goes through an imine intermediate because it adds the equivalent of a primary amine, NH2, primary amine, NH2 with another thing attached, and then it undergoes a later removal of nitrogen in the process of getting protonated and reduced. So I'm not going to go through all the mechanisms here in detail because that is the part of the chem activity, but I would like to talk about the Wolff-Kishner reduction in a little bit more detail. Okay, in the Wolff-Kishner reduction we are indeed in base. If we do it all at once, we can do it in two steps as well by making the imine and then adding the base, but I'm going to just show the mechanism for being in base. So in base, and you have a decently strong nucleophile, you don't have to worry about having negative charges. The first step of this reaction involves one of the nucleophilic nitrogens of the hydrazine, the NH2, approaching the carbonyl carbon, then breaks, putting the extra electrons on the oxygen atom. This gives us our first intermediate. We then do a series of acid-base reactions separately. That is, a base comes along and takes off the proton that's over here, and an acid in solution, such as another hydrazine molecule or water, comes along and adds a proton right here, and we end up with a neutral intermediate. We then kick out a hydroxide leaving group, and again, hydroxide itself is not a very good leaving group in that it's a pretty strong base, but we already have bases equally as strong in solution, hydroxide, so it's no stronger than other bases in solution. This creates a new intermediate, which is quite acidic for this solution and will immediately be deprotonated by the hydroxide you just kicked out, or another hydroxide in solution. This provides us with our imine intermediate. Note that this imine looks very much like the imine up here. In fact, it's the same intermediate. But in the presence of strong base, we don't stop here. In the presence of strong base, one of the protons we can possibly remove, especially with heat, is the hydrogen on the end of the hydrazine to create our first carbanion. This carbanion is resonance stabilized. It's much like an enolate ion, but it can protonate at that position from a hydrogen in solution, such as another hydrazine or a water molecule you just created during your deprotonation, to create the first reduction product. This compound can then undergo the same process all over again, first removing the acidic hydrogen from the terminal nitrogen atom, this time creating a triple bond end breaking the last NC bond and creating a new carbanion. Once again, this carbanion will be a strong base and willing to accept a proton from an acid such as the water that was just created to give us our final reduced product plus nitrogen gas plus an equivalent of water. To make this a little easier to see, I've now color-coded the nitrogens and hydrogens that come from the hydrazine throughout the mechanism. You can now see that the hydrazine delivers the net 2 of its hydrogens to make this new bond. The other 2 hydrogens end up combined with the oxygen that was the carbonyl, way back here, went off as a hydroxide, but eventually gets protonated twice, and so ends up being the water molecule.